Welcome to the Journey Chez Chem. Well, let's review what we've learned and do the best you can, and I'll see you in a moment. In number one, I first asked myself, is this a weak acid or a weak base? Well, ammonia is a weak base, and therefore I must go through the process of determining what is the amount that has been dissociated. Well, ammonia normally acts as a weak base. And yes, yesterday we learned that it could also act as an acid. However, in this case, because I'm given a Kb, I know that it's acting as a base. Well, I add water, and therefore, if we were looking at Bronsted-Lorwry theory, the ammonia is accepting a proton, and therefore it is a base. And water is losing a hydrogen, and therefore it is an acid. Well, I'm given an initial concentration of 0.42 molar, and I have no dissociation initially. Then I know some of it will dissociate. And I will get the same amount of both of the ions because it is a one-to-one relationship. Then I have 0.42 minus X. I carry these down in my ice chart, initial, change, and equilibrium. And I also have X of each one of the ions. Well, I know that my Kb is equal to the products over the reactant. And I do not include water because it is a pure liquid. And therefore, both of these values are X, and that gives me X squared. And I put it over 0.42. Now, I eliminate this X value because I am going to assume that it is less than 5% dissociated, the 5% rule. And then I set it equal to the Kb. Once I do that, then I can solve for X. I multiply 0.42 times the constant and take the square root. And my X comes out to be 2.7265 times 10 to the minus 3. And I'm going to round it to the hundredths place. Therefore, it is 2.73 times 10 to the minus 3. Well, what does that X represent? It represents the hydroxide as well as the ammonium, but for pH, I'm interested in the hydroxide. It is the molarity of the hydroxide ion. I'll just erase this part to give us more room. Molarity of the hydroxide ion. Then, when I take the log, the pOH is equal to minus the log of the hydroxide ion concentration. And this is the concentration. And when I take the log of it, I get the pOH. And therefore, in this case, the pOH is 2.5638. And I always round this to the hundredths place. And therefore, my pOH is equal to 2.56. The 3 does not round the 6 up. And the pH plus the pOH is equal to 14. And therefore, my pH is equal to 11.44. That's the first part. Then I want to make sure, and I'm also asked what the percent association is, or the percent ionized. And therefore, I want to find out how much of this was changed into its ions. So I take my amount, and it doesn't matter if it's a hydroxide or a hydrogen, I still take my X value, which will be 2.73 times 10 to the minus third, divided by my original amount times 100. And when I do this, I get 0.6500, and percents are always taken to the tens place. And therefore, I have 0.7% dissociated or ionized, and therefore it is well within the 5% rule. Yesterday's warm-up, we had a weak acid. Today's warm-up, we have a weak base. Therefore, we've done every type of problem that you may see on this type of question. And that's how you do number one. 2, we are using the Bronsted-Lorwry acid-base theory. And whenever you see the word conjugate, then that indicates it's Bronsted-Lorwry. And in Bronsted-Lorwry theory, the acid is a proton donor, and the base is a proton acceptor. So I look at my equation and I see, well, a proton is my hydrogen ion, and we discussed how the hydrogen ion, all that's left with the hydrogen atom is the proton, so that's why we call it proton. Well, when I look here and then I look here, I see that it actually accepted a proton, which would not be an acid, that would be the base. A base will accept a proton, and then wherever it is with that proton is called the conjugate acid. Then we know that the other compound must be an acid, but let's look at why it's the acid. It is an acid because it has given up this hydrogen, and here it is without the hydrogen, and that would make this the conjugate base. And if I was going in reverse, I could see this is my base because it is picking up a hydrogen here, and that would be my conjugate acid. Now for us at this level, the acid and base will always be a reactant, and the conjugates will always be the products. But that is not necessarily always the case because they are acid-base pairs. In the second case, I see here that this compound has lost a hydrogen over here, and therefore this is my acid, and this is the conjugate base. This is the base because it accepted a hydrogen. This is the base. This is my conjugate acid. That's the Bronsted-Lorwry theory. And now you have a little bit more practice on this, then we'll have a review, and then you'll be ready for the assessment, and that'll be the last of the topics, and then you'll be ready for the semester exam. I know you do well. We've been having so much fun. Well, I can't wait to see you tomorrow. Bye.